So now we are going to do the Python coding part of this problem. And to start off, I have already entered in a few imports that we need for this problem, including numpy as np, the solve IVP function from SciPy integrate, and we need that in order to solve our differential equations that we found in part 1. And then we also need plotly in order to plot our solutions. And then I also just made the plotly plot dark, just because it looks better that way. So to start off, I'm just going to be entering in these given values that we have. So Q will equal 100. C equal 1. T in will equal 350. V will equal 100. Rho will equal 1,000. Don't want that. C equals 0.239. HR 5 e to the 4. $50. Oh my gosh. Alright, so I think that's all the initial values that they give us for this problem. So one more thing that I forgot that we need is our variable that we'll be changing, which is tc, and we're just going to start that at 300. So now we can define a function, and we're just going to call it RHS for the right hand side of these equations that we made. And we're going to be inputting time and then some vector of multiple things. And now we can unpack that vector, and it will be the concentration of A, which I'm going to do lowercase, and temperature will equal that vector. And then what we will be returning is the right-hand side of these equations. So I'm going to type those in. Q over V times Cn minus Cn. I will actually make this capital. Cn minus Ca. Minus K times Ca. And we will have to define K later inside this equation using this. But for now it's okay. And then our second equation is also Q over V. T n minus T minus UA over rho times V times C. I'm just going to put parentheses around everything just to be safe. And then that is also multiplied by T minus TC. Yeah, and then plus negative HR times K times CA over, where's that, rho times C. And now we will define K as well. K will equal K naught times exponent activation energy over, like so. And it looks like these V's should be capital as well, because that's what I defined it as before. Capital V, capital V. There we go. And then one more thing I forgot is brackets around this because it will be an array as well. Also, just to make sure that this doesn't mess up, I'm going to put parentheses around that as well. There we go. Now we can actually use our solve IVP function. And first we need to put in our right hand side function. And then we're going to want the times that we are starting at. So that'll be from 0 to an end time, which I'm going to define that as like 10 minutes. And then we need our values, so that'll be our CA naught, and where's our other one? T naught. Then our method will be radu. And since output will equal true. This needs to be inside brackets as well. Solve by VP. So I'm just going to run all. And then we are going to want the solution from right here. I'm just going to put dot sol here. So now we have our solution from our solve IVP function. So now we're going to start working on plotting this. So first I'm going to define this just as the solution. And we're going to want that to make that equal to our concentration, temperature will equal our solution of, and we're going to make a list of temperatures for plotting purposes. So those are going to be linear space temperatures, p dot lin space, and we're going to start at what, like 0, and then go to our T end and do about 500. I don't think there we go. Now we're going to work on plotting this. So I'm going to go fig equals make subplots. And we're going to want two side-by-side plots since they're in different units. So we're going to do columns 2 and rows 1. And then we're going to go fig add scatter. And we're going to want the x's to be our t plot, and the y's, in the first case, will be our concentration. Set the mode to ones. And then we're going to want this in column 1, row 1. And I'm also going to name it as well. Concentration. And then we're just going to want to do that again. But this time with our temperature. Right here. We want this in column 2. And actually does not look right. There might be a typo up here in this equation. Yeah, so this is just plus HR. So now we can see what it does with different cooling temperatures. So the best one is 305 as our cooling temperature. Then we get a really interesting graph where the concentration of A starts up here at 0.5, like we said, and it drops down almost immediately and keeps going on these little spikes. And then the temperature starts at around 350, like we said, yep. And it spikes up right in the beginning and then goes on a few spikes like this as well, which this is definitely the most interesting condition. But we can also look at it if it's at like 295. And this is kind of less interesting, but it would just start at that 0.5 initial concentration and just increase. And then the temperature will start at our 350 and just decrease all the way down. So I'm just going to leave it at this 305. And there we go.